Have you ever wondered how we take something as unimaginably vast and complex as the Earth's climate and literally squeeze it down to fit on a school desk? Well, today we're exploring exactly that. We're going to dive into the really fascinating ways educators use simple classroom experiments to model our entire atmosphere. But we're not stopping there. We're also going to unpack a recently published scientific debate over whether these miniature classroom models actually replicate real-world physics. It's an incredible look at how we learn, how we teach, and honestly, how science constantly questions itself. Let's get right into it.
Just to give you a quick roadmap of where we're headed, we'll start off by building our Earth in a bottle, then explore the albedo effect and simulate some greenhouse gases. After that, we're going to pivot and look at a methodological critique of these closed systems, break down the actual physics of radiation versus conduction, and wrap up by weighing the true value of scientific models. Section 1. The Earth in a Bottle, Simulating the Atmosphere. So to understand how educators introduce massive planetary concepts using everyday stuff, we first really need to define what they're trying to demonstrate. The greenhouse effect is at its core the physical process where atmospheric gases allow visible sunlight to pass right through, but then they absorb and re-radiate the lower energy infrared radiation that bounces off the Earth's surface. Basically, think of the atmosphere acting like a giant heat-trapping blanket. And, as our sources remind us, without this natural warming blanket, life as we know it simply couldn't exist here. This brings us to a classic classroom setup that brilliantly brings this massive concept to life. Imagine simple, clear plastic bottles. Students pop a thermometer inside, maybe add some soil, water, or even ice at the bottom to represent the Earth's surface. That clear plastic shell, that's the atmosphere. When light from a lamp, or just the sun, passes through the plastic, it warms up the stuff inside, and the trapped air gets hotter. It's a super immediate visual way to show students that a contained environment traps heat, kind of like our real atmosphere does. Section 2. Exploring the albedo effect, reflection versus absorption. Now, before we go pumping greenhouse gases into our bottles, there's another absolutely crucial climate mechanism taught through these models, the concept of albedo. Albedo is simply a measure of how strongly an object reflects light from a source, like the sun. It's the exact percentage of incoming light that bounces back into space rather than being absorbed. Some light gets absorbed by the Earth, which warms things up, while some just reflects away. For context, our planet's average albedo is estimated to be right around 30%. In the labs, students test this out by comparing high and low albedo surfaces. A high albedo surface, think snow or ice, reflects a ton of light. Students might test this using white paper or light-colored sand. On the flip side, a low albedo surface, like a blacktop road or a really dark forest canopy, absorbs way more light and turns it into heat. To measure this, you typically put thermometers inside black and white paper envelopes under a lamp. The black envelope, our low albedo surface, heats up significantly faster, proving right before your eyes that surface color dramatically changes heat absorption. Section 3. Simulating greenhouse gases, pumping up the CO2. Okay, so let's see how all this builds into demonstrating the impact of specific gases, which is the absolute core of global warming simulations. The procedure is actually surprisingly simple. Students set up two identical containers. Container A is the control, just regular room air. But in container B, the experimental one, they generate carbon dioxide. A super common way to do this is by mixing good old vinegar and baking soda right inside the bottle, or maybe dropping in an effervescent tablet, which rapidly releases heavy CO2 gas. Then, both bottles get placed right under a strong heat lamp at the exact same distance, and students measure the temperature changes over time. What happens next is pretty striking. You have the initial setup, and then the aftermath under the heat lamp, where a chemical reaction is bubbling away in the bottom of the experimental bottle. Across these experiments, students consistently record that the bottle enriched with carbon dioxide reaches a much higher temperature than the control bottle with normal air. The conclusion drawn in the classroom? The added CO2 trapped more heat, simulating exactly how rising emissions warm our real atmosphere. Section 4. The closed system critique, a methodological twist. And here's where things take a really fascinating turn into the scientific method itself. The big, crucial question is this. Do sealed plastic or glass bottles actually mimic the physics of the open sky? It's a fantastic question to ask. We know the model works conceptually to introduce the idea of heat trapping to kids, but from a strict, rigorous physics standpoint, does a plastic barrier behave identically to millions of miles of open gas? Enter Michael Nelson's published critique.
Nelson constructed a highly specialized experimental setup to objectively measure whether the heating we see in standard bottle experiments is actually due to greenhouse gas absorption or if something else entirely is going on. His critique focuses purely on the physical mechanics of this closed system laboratory setup. To fully grasp the weight of this critique, we kind of have to zoom out and look at the history. This experimental design isn't some new trend. Back in the mid-1800s, Eunice Newton Foote famously used glass cylinders filled with CO2 and exposed them to sunlight, noting higher temperatures. Modern classrooms just adapted her method using plastic bottles and desk lamps. But now, Nelson's 2025 publication challenges this 150-year-old methodology using modern infrared detectors. He argues that Foote and educators today completely overlooked a critical physical barrier in their testing.
Section 5. Radiation versus conduction. What are we measuring?
Let's break down the exact scientific distinction Nelson makes. In his paper, he states his findings pretty boldly. He writes, "The conclusion was that the conventional greenhouse effect laboratory experiments using closed systems failed to prove the greenhouse effect theory." Now let's be absolutely clear here. Nelson is not debating the reality of climate change. He is specifically stating that the classroom bottle experiment itself fails to scientifically prove the mechanism of the greenhouse effect. Let's look at exactly why. It all comes down to a fundamental mix-up in physics: thermal heat transfer versus infrared radiation absorption. Think about a physical greenhouse, or our plastic bottle. The solid container absorbs the light from the lamp, heats up, and then warms the air inside through direct physical contact. That's called thermal conduction. Plus, the solid barrier stops the hot air from mixing with the cooler air outside in the room. But the actual atmosphere doesn't have a giant glass roof. It relies on specific gases floating in the open sky, absorbing low-energy infrared radiation emitted by the Earth. Nelson argues these are two completely different physical processes. To prove this, Nelson modified the experiment. Instead of a high-energy sun lamp, he used a heat plate that emitted infrared radiation to mimic actual Earth surface temperatures. His findings? Absolutely fascinating. First, standard thermometers only measure overall temperature, not radiation absorption. Second, he discovered that the plastic or glass containment barriers themselves absorbed a whopping 98.3% of the infrared radiation. The container was doing the heating, not the gas. In fact, when he tested non-greenhouse gases like nitrogen and argon, they heated up just as much, if not more, than the CO2. The containment membrane was basically obscuring any measurable absorption by the gases inside. Section 6. The value of models, synthesis, and science. So, where does this leave us? Do we just toss the classroom bottles in the recycling bin? Not at all. This actually beautifully illustrates the dual nature of science and education. Models are inherently designed to simplify reality. That bottle experiment is incredibly effective at introducing the concept that altering an environment's composition can trap heat. It's a brilliant cognitive stepping stone for young learners. But at the same time, rigorous critiques, like Nelson's, are absolutely essential for researchers to ensure that when we claim an experiment proves a specific law of physics, our methodology is actually flawless. And we always have to connect the model back to the reality it represents. Even if a sealed plastic bottle relies on thermal conduction rather than true infrared absorption, the real-world planetary-scale phenomenon is extensively documented. When you look at the data over the last century, global temperature anomalies and rising atmospheric carbon dioxide levels move almost exactly in tandem. The correlation in the open atmosphere remains a heavily documented reality, completely regardless of the physical limitations of our little desktop lab setups. Which leaves us with a really exciting challenge as learners. If a closed bottle isn't a perfect physical replica of the open atmosphere, how can we design better, more accurate physical models to understand complex planetary systems? Can you think of an experiment that isolates infrared absorption without a container getting in the way? It's exactly this kind of questioning that drives science forward. Thanks so much for exploring this with me today. Keep questioning and keep learning.